All right, let's take a look at some more Chapter 5, Webassign problems. I would like to do at least a few here. I'd like to get 3 more done. And the ones I'm looking at, number 8, number 9, and number 13. Let's see if we can do those. Okay. So let's take a look at 8, 9, 13. These are all circular motion problems, right? So I'll write down the rules really quick. How do we do force problems? We need to draw a picture, and since these are circular motion problems, our picture must include the circle. I'll make a little note here. And when we draw the circle, we need to label the radius. Then what do? We need to pick an object for a free body diagram, right? When we do that, we're going to make it a rectangle. And that rectangle is going to be oriented the same way as the object. We are going to label forces on that rectangle. And then what are we going to do? We are going to define axes. And remember, our one rule for axes is one axis must point in the direction of acceleration. And so for a circle, circular motion, the direction of acceleration is, remember, toward the center. So when we define our axes in a circular motion problem, one axis must point toward the center. Then what do? Then we split forces into components where necessary, and then we write F equals ma for each axis. That's pretty much it. That's how we do free body diagrams, right? And then at the end, if we're doing circular motion, we are also going to include that the acceleration is v squared over r. That's an extra equation. So the rules are exactly the same as the normal force problem rules, but when we are doing circular motion, we just make sure that our picture includes the circle. We make sure that one of our axes points toward the center of the circle, and we also just include acceleration as v squared over r with our equation. That's it. So what do we have for problem 8? Problem 8 gives you a pole, and they tell you that there's a ball here, and it is attached to the pole by these 2 wires. I'm going to call this wire number 1, and this, of course, is going to be wire number 2. And they give you, this is length L, this is also length L, and they give you, I'm going to call this right here height H, and I'm going to call this height H. They give you those. So here's our picture, and what you're told is this guy is swinging around, kind of like a tetherball, except it also has a wire here. So we're going to do this, and here is going to be the circle, like this. In addition, I'm going to label his speed v, and what they give you is they give you the speed. So the speed is known. I'm going to label this as radius r, and r is not known. Here we go. They give you his mass, and that's it. And what they want you to do is find the tension. They want you to find T1 and T2. How do we do this? It is a circular motion problem. The circle is horizontal, it's right here, and here is the radius. I'm going to go ahead and do this. I'm going to call this angle, I'll go ahead and call this angle theta, and this is also angle theta, right there. What I would recommend you do, because you have H and you have L, go ahead and use H and L. Notice there's a triangle right here. Use H and L. Go ahead and get R, and go ahead and get angle theta. You're going to need both of those anyway. So you've got R and theta. Now what? Let's do a free body diagram on this guy. We're going to do a free body diagram on the ball. What forces are acting on this guy? Always, always, always gravity. Gravity always straight down. What other forces are acting on him? What is touching the ball? Wire 1, wire 2. So I'm going to go here. This is going to be T2, and I'll go up here. That's going to be T1. You should be pretty good at doing free body diagrams, and they're very simple. Rectangle, draw forces, gravity, anything touching. That's it. But now what? Define your axes. One must point towards the center of the circle. The center of the circle is that way. So let me get rid of this. So we're going to define x this way. We're going to go ahead and put y perpendicular to it. And now we need to split forces into components. mg is okay, but I need to split up T1 and T2. That means I need to turn them into triangles. So which triangle am I going to draw for T2? The lower triangle or the upper triangle? Notice the upper triangle matches my picture. So it makes sense to use the upper triangle. And notice then this angle right here is angle theta. Same thing for T1. It makes sense to use the lower triangle because that captures this. So I'm going to go T1 here, like that. And this is my angle theta. Great. Write your equations. X equation, Y equation. What is X equation? Everything this way is positive, everything over here is negative, but there's nothing over here. So I have this pulling positive, this pulling positive. What is this guy? It is T1 sine theta, because it's opposite the angle. And this one is T2 sine theta. And those equal ma, because that is the direction of acceleration. What about the y equation? I need everything up minus everything down. The only thing up is T1 cosine theta. Down I have T2 cosine theta, and I have mg. Also, a is v squared over r. How many equations do we have here? 3. How many unknowns? 3. A, T2, and T1. You have V, and you have R. Now, it's your choice. You can, if you want to, you can calculate A, because you have V and R. It's up to you. Or you can just replace it algebraically. I'll just assume that you're going to calculate A, and that's fine. It's okay to calculate A. Sometimes you're asked to find the acceleration. It's an unknown. May as well go ahead and get it. But then how do you get T1, T2 out of this mess? I am going to rewrite these equations. I'm going to divide this first one by sine theta, and what I'm going to get is T1 plus T2 is equal to ma over sine theta. I'm going to add mg to this side and divide by cosine theta, and I get T1 minus T2 is mg over cosine theta. How do you solve for T1 and T2? This is a classic algebra situation. You have x plus y equals constant. You have x minus y equals a constant. What happens if you add the equations? I'm going to leave it at that. If you add the equations, on this side you get this thing plus this thing, right? All known values. What happens if you add here? These go away, and you get 2 T1s. What happens if you subtract the equations? This equation minus this one. On this side, you have this guy minus that. Here you have T1 minus T1, T2 minus a minus T2. Very quick and simple. If you add equations, subtract equations to get what you need here. All right, I'm going to leave that one where it is. Moving on. Want to take a look at Tarzan, number 9. Number 9 says, Tarzan has a mass of 85 kilograms. He tries to cross a river by swinging from a vine, right? The vine is 12 meters long. His speed at the bottom of the swing is 8.2 meters per second. Tarzan doesn't know that the vine has a braking strength of 1,000 newtons. Does he make it safely across the river? So this is a yes or no question. But we know to ignore the yes or no and instead find the information that will allow us to answer that question. Same thing that we had back in chapter 2 when we had the jet landing on a runway and they asked, is the runway long enough? Well, what did you have to do? You had to find how much distance the plane needs to stop. You had to find that x2 in your motion in one dimension problem. Once you knew how much distance the plane needed, then you could decide whether or not the runway was long enough. So this is the same kind of situation. What we need to do is find the tension in the vine. And here's the idea. This is the trees, and the vine is here. Now, this is our first instance of something that I call things that swing from strings. And we are going to do a lot of things swinging from strings in these upcoming chapters. A couple simple principles. When something swings from a string, and it could be a vine or a rope or a wire or whatever, one end is fixed. That's important. The other end has the object. So as the object swings, every point in their motion is the same distance from this fixed point. By definition, they are going in a circle. The definition of a circle is the collection of points that are equidistant from a given fixed point. So, by definition, the object is in circular motion. A vertical circle. Right? When he swings, he is basically tracing out a vertical circle. He's in circular motion. The length of the string is the radius of the circle. In this case, the length of the vine is the radius of the circle. So Tarzan's going to come down here, and now they're talking about they give you his speed right here, and they want you to find the tension in the vine. They give you his mass, they give you the speed. This is a circular motion problem. It's really important to recognize when you have a thing swinging from a string, it will be a circular motion problem, right? What can we do with this? Free body diagram on Tarzan. We're not going to overthink this. Not going to overthink anything in this class. Force is acting on Tarzan. Gravity. What's touching Tarzan? The vine, and that's it. Great. Got our forces. We need an axis. What does the direction of our axis have to be? Towards the center of the circle. The center of the circle is right here. I'm going to, how you can put it. This is the center of the circle. So one of our axes has to point upward. The other one, I can point to the right. We don't need to split up any forces. What do we get? X and Y. X, we have nothing. Y, we get T minus mg equals ma. And of course, we have A is V squared over R. Just like that. Do not calculate V squared over R. You don't need it. Much easier to just put V squared over R into here algebraically, right? Save a calculation. If later you decided you needed to calculate A, you could. But I'm usually against doing unnecessary calculations. In the previous problem, I told you go ahead and calculate A if you want to, right? Kind of on the fence there. This one, not even worth doing. Put V squared over R there, add mg to the other side, calculate your tension, done, out. So this is a simple, Tarzan is a simple force problem, simple circular motion problem, but it's actually the kind of problem that we're going to see coming up in the next few chapters because we're going to have things swinging from strings. And at the bottom of their swing, you'll have mg, tension, just in a line. Nice, simple situation. Right? Hopefully some of these problems, you're getting the hang of it, right? It's going a little smoother than it did, say, in chapter 2. Hopefully you're starting to feel like you're getting in the groove, so to speak. You're working with some of these. So, speaking of, let's pick apart number 13, because I think number 13 is the sneakiest of the bunch. I mean, it's still, you just follow the rules and do what you're supposed to. But in problem 13, they've given you a picture which I think is a little bit misleading, and they're not being helpful. I think they're trying to be helpful, but it's not helpful. So I want to talk about number 13, make sure you guys know what you're going to do with it. Holy moly. Oh, 15 minutes, okay. I thought my clock said 35 minutes already. I'm like, oh. So number 13 says you have a model airplane, and they give you the mass. It flies in a horizontal circle at the end of a 60-meter control wire with a speed of 35 meters per second. Find the tension in the wire if the angle that it makes with the horizontal is 20 degrees. So I sort of paraphrased there. They've given you what you think is a picture. It is not. What they have given you with that problem is not the correct picture. I'm not saying they did this on purpose to try to deceive you, but it's just not what you're supposed to do, and that's extremely important. There's a tendency to believe that if something is published, then it must be correct. That if somebody who wrote this problem did this, then it must be correct. And that is so completely untrue. All of these things are made by humans, and humans make mistakes. Humans do things in ways that are not ideal. Humans do things in ways in which they cut corners, especially when those humans know what they are doing. They're more inclined to cut corners. So it's very dangerous for you doing this stuff for the first time to assume that anybody else that does it knows what they are doing. Quite frequently, they do not. In fact, it's been my experience that roughly, and I'm not talking about students in my class, I'm talking about people who should know better. People who supposedly know how to do this stuff. I have found that roughly 90% of them do not. You would think that people who are physics majors know how to do this. No, they don't. You would think grad students in physics would know how to do this. No, they do not. And I was guilty of that myself. I did not learn how to do all this stuff properly until I spent several years as a grad student and then several years as a lecturer, and now I've spent the past 20 years at RCC. It took years for me to get the details down. And that was after I already finished my degree as a physics major. So very, very important for you to realize what I'm sharing with you is decades of my experience in observing just how bad people are at doing this stuff. So when you see something attached to a picture, attached to a problem like this picture, you may be inclined to want to mimic that, to imitate that. Absolutely one of the worst habits that you could have, to look at the work of somebody else and automatically think that you should be imitating that work. Don't. You should be creating your own work, and you should know why you are doing your work the way that you are doing it. In this case, I am telling you how you should be doing it. I'm not having you copy my work. I'm giving you the instructions to create your own work. Other people's work. So what do we have here? We have a plane, and it's flying at the end of a control wire. So I'm going to draw my control wire. I'll go ahead and do it like that. There we go. And then it's attached to the wing. So they give you this. And I'm going to draw the picture so you can actually see what's going on. This is the back end of the plane, okay? So you're looking at the plane from behind, and the wings are tilted at this same angle, which we're going to call angle theta. So this is, the wing tilt is angle theta. This is our picture, but we need more because we need to be able to see the circle. Now they give you this length of the wire. They give you the length of the wire here. But the circle that the plane flies in is like this. The wing is being held, but it's circling around like so. So the radius of this circle is right here. And that's the first thing I want to impress on you. You need to be able to see the circle in your picture. The little picture they gave you does not have a circle in it. It's not correct. You need to be able to see the circle so you can see the radius. Once you do that, what you should notice is this. This is angle theta. This is also angle theta. And you have a triangle here, which means R is L cosine theta. You have to be able to see those kind of things in your picture. Now what? Well, they tell you the speed. So he's going around with speed 35 meters per second, and they give you his mass, and they want you to find the tension. It's a force problem. How do we do this? Follow the rules. So, what do we do with this? Always, when you draw your rectangle, it's always oriented the same way as the object is in the picture. In this case, the plane is tilted. Usually we have a tilted free body diagram because the object's on an incline. But in this case, it's tilted simply because the plane itself is tilted. And that's fine. The rule is you draw the rectangle oriented the same way as the object, regardless of why the object is oriented that way. So now we have a rectangle. It's like this. Oh, I'm going to put my angle in here. This is the angle of my tilt. Great. Forces, always, mg. Straight down. What other forces are acting on it? Well, the tension is pulling that way, and that is the same direction as the bottom of the rectangle here. So I'm going to go like that. What else? You're told there's a lift force. The lift force is perpendicular to the wings. Well, these sides of the rectangle are parallel to the wings, so these sides are perpendicular to the wings, which means you can just extend this side of the rectangle, and I'm just going to call it F lift, kind of like what they did, I think. We just don't want to, I have L for the length of the wire here, and I don't want to confuse this L with the lift force. Anything else touching this guy? No, the only thing touching him is the tension, is the wire. But you could also argue the air is touching him. The air is causing the lift force. That's it. What's next? Axes. One of our axes must point in the direction of acceleration, which is toward the center of the circle. And here's where this one's sneaky. Usually, if we have a tilted free body diagram, we have tilted axes. Because usually it's because an object is on an inclined surface, and that's the direction it's accelerating. But in this case, we have a tilted object that is moving in a horizontal circle. So our direction of acceleration is that way. And that's fine. That's fine. Follow the rules. You just have to follow the rules. I promise you, if you simply follow the rules, every single problem, boom, drops right out. What's next? Split forces into components. Here's your X and Y. mg in this case is okay. It's on the y-axis. Done. Who do we need to split up? Tension and lift force. How do we do it? We need a horizontal and a vertical component. I'm going to turn this into a triangle. Actually, let's get that. I'm going to go here and here. I need an angle for this triangle, but notice this is angle theta. This is also angle theta. They're vertical angles. You should be able to clearly see that right here if this diagram is drawn well. And so this is angle theta. Now I need to split up my lift force. Now that's a little bit trickier to see, but I'm going to do this to help you out. This is also angle theta, right? And so I am going to draw, actually I'll just do it this way. Here's my right angle. This is 90 degrees. This whole thing is 180, which means this angle and theta add up to 90. If these two add up to 90, that means this must be angle theta. These two are complementary, so these two are complementary, so these two are the same. You're going to have to do a little bit of geometry sometimes when you do your triangles, but make sure you can clearly see why the angles are what they are. What do we now do? Write your equations. What do we have for our equations? X equations. Everything this direction. Everything this direction minus everything this direction. There's nothing over here. So what do we have? We have the lift force, which I'm just going to leave off the lift. I'm just going to call it F. F sine theta plus T cosine theta. That's it. Just this guy and this guy. Only things pulling this way. Equals ma. What about the y equation? Everything up minus everything down. What do we have for ups? Lift force component. That's it. So we have F cosine theta, and then down we have T sine theta and mg. And then we also have A equals V squared over R. Now, I would say in this case, it's also just like when we did problem 8. Good idea, go ahead and calculate A. It's fine. It's an extra little calculation, but calculate R, right? Go ahead and calculate R, and then go ahead and calculate A. Usually I'm not a big fan of doing a lot of superfluous calculations, but it will help simplify things a little bit in this case. How do you finish this up? Recognize that you have just two equations, two unknowns. And it looks a lot like problem 9. But in problem 9, we had sine, sine, we divided by sine. We had cosine, cosine, divided by cosine. Now you've got a sine and a cosine and a cosine and a sine, but it's still very similar. So I'm going to do this. I'm going to have F sine theta, right, plus T cosine theta equals ma. And I'm going to have F cosine theta minus T sine theta equals mg. I'm going to recommend that you divide everything here by cosine theta, and you divide everything here by, actually don't even bother to do that. Divide everything here by sine theta, and then divide everything here by cosine theta. Here's what I would do. I would go F plus T cosine theta over sine theta equals ma over sine theta. And then here I would do F, divide everything by cosine theta. So you'd have T, this actually just becomes tangent theta, equals mg over cosine theta. Then what I would do is I would subtract equations. I would then subtract the bottom equation from the top one. If you do that, you're going to have T, you could write this as T divided by tangent theta if you want to, but you'd have this plus this equals this minus this. And the f's, of course, drop out. And at that point, you can factor out T, so that you'd have T times this equals this thing minus the other thing. Divide by that, calculate your T, you're done and out. All right, I am going to shut this down before we get to the 30-minute mark. As always, any questions, any issues, anything giving you any trouble, let me know. And hopefully this will help you close out Chapter 5. All right, thanks.